find these vortices, provided you give sufficient omega to this equation. So, and we consider here a potential that has quartic and quadratic terms. Here is represented in more involved form, but for sigma equals 0, you have x quarting just in x quarting direction. So you can make a trap, a quartic trap just in x direction or in xy direction. So in principle, you can confine just in one dimension. So we performed calculation in both situations. Think that maybe experimentalists can do them in both situations, either quartic trap just in x direction or a quartic trap in x and y directions. So let's analyze first just the x quartic confinement, and then this potential is in this way. In fact, we have a quadratic term in the y direction. We have a quadratic term in the x direction, but we have a minus inside it. And this minus is to force, it will be more clear later why we have this minus. In fact, it is to force things to break up. But later on, we can make this a equals 0. So maybe at the beginning, it looks artificial. Okay, of course, if you do a minus, you have an inverted trap. And of course, you can separate things in the x direction with this. But later on, we can make it 0. And then we have this quartic trap, this b square x4 quartic trap, and then an extra term just to make it easier, the calculations. So if you choose I equals 0, this is just a double L. So a double L, if you start with a double L, and it already make it easier to separate the condensate. So of course, when you start to rotate it, it will make it even easier to make the breakup. So for analyzing this, we make a Thomas Fermi approximation. So this is a special kind of Thomas Fermi approximation. Thomas Fermi approximation, usually you just drop out the kinetic energy. And once you drop out the kinetic energy, the nonlinear equation, nonlinear Schrödinger equation, or the Gross-Pitevsky equation becomes much simpler, and you can throw to the other side all this part and make this psi square equals to mu that here I call Thomas Fermi over G. But you see that because you have this omega of Z, you now have an extra term omega square R square over 2, because you consider that omega LZ you can replace like a solid body rotation. This is well justified by Fetter in his review article 2009. So once you have this density psi square, this density must be greater or equal to 0. Of course, density cannot be negative. So density equal to 0, it defines the border of the Thomas Fermi approximation, because once it is 0, it defines the place when you at some side you have no condensate and the other side starts the condensate. And this must satisfy the normalization condition. Also, you must integrate psi square so as it will give the number of atoms. Well, depending on number of atoms or 1, depending on how you characterize the G constant. You can make the G, you can multiply G by n and then you normalize by 1, or you can make it G and normalize by n. This doesn't matter. It's equivalent form of describing. You can normalize the wave function of the condensates to 1 or to n. So you have in the lower line n naught equal n is defined by the density in the center of the trap, and this mu Thomas Fermi minus V sigma 00 over G, and equals to 1 over G mu Thomas Fermi. Here mu Thomas Fermi, and here you have A square over B square. And at the breakpoint, you must have N naught. The density of the condensate must be 0 at the breakpoint. Of course, when you stretch the condensate and finally it starts to break in the middle, you should have the density equals 0. So from here, you immediately obtain an analytical result that will be very important for us, that the mu Thomas Fermi is equal to A squared over 4B squared, A4 to the 4B squared. Okay. No. Okay. So the contour of this, as I said, you have a double well, and the contour should be, at the contour it should be, the density must be 0. And before and after the breakup, I will show very nice figures in a minute, they are similar to Cassini ovals, so you can do it analytically. And if you look at the internet, you see what Cassini ovals is there, and is that these shapes, depending on the parameters A and B and some parameters, you have exactly, these are well-known structures named Cassini ovals. And just at the breakup, the contour curve can be identified. It should be this one, sorry. The contour curve, this is the point where you have break-on. In the third figure, here one, you must have exactly, this is the breakpoint. And this figure, this is a kind of Bernoulli-Lemniscate. These are well-known geometrical figures that we later on we find this, understand these figures, geometrical figures. So for doing the analysis, the analytical analysis, we performed it in polar coordinates. So x and y, we switch it to r and theta, and the contours should be at r theta. So breakup can identify it with the absence of real solutions at theta equal pi minus or plus pi over 2. So of course you cannot have any solution to this in these angles, and also because I will show you go to B-quadratic equation, you have two solutions. One is, we call it r minus, and here we call it r plus. And here is theta, and here is r. And I will show you, this is the kind of expression we found when you replace the Thomas Fermi approximation, we replace in polar coordinates, you find these expressions, and then you find r minus and r plus, and you should look at these conditions when the density is 0. So within the Thomas Fermi approximation, the critical, because we exactly at that point, we know the Thomas Fermi, the mu of the Thomas Fermi, we could obtain exact analytical rotation for breakup. And it is obtained as this GB to the power of 4. Then you have this fancy integral where theta m is something that looks complicated, but at the end, you can do it analytically, and we find a very unusual expression, and we see, let's see if it's true. What we did, we take this expression, this GB to the GB to the power of 4 with all these parameters. Omega s is the the omega that gives you the breakup is omega split. It's exactly the omega that makes the breakup. And we build this plot for two kinds of parameters, for A equals 0, as I told you, and for A equal 0.5. So for A equal 0.5, we made this, some studies, then we do full numerics for these 4 points, and then we make full numerics for these 2 points. So as you see, we must, when you cross this region, we must have breakup at this, exactly this point. So let's see if our variational approach is true. So we run it for omega 0.3, and we obtained this figure. So this is the, in colors we have density, and here we have the contour given by Thomas Fermi. So inside is full numerics with the vortices, and outside is the Thomas Fermi approximation. So in all these cases, as you see, as we increase the omega, we start, and finally we have breakup between omega 0.5 and 0.6. This is exactly the point as I showed you. The point here is exactly between 0.5 and 0.6. So we predicted from our analytical approach that we have breakup here, and this is being satisfied exactly as we predicted from this figure to this. Note how nice it is that in the end it starts to appear a single vortex in the middle, and finally the single vortex, they detach through this single vortex. And here I show in y equals 0 comparison between full numerics of Gross-Pitaevsky equation and Thomas Fermi approximation. And you see how the contours around y equals 0 for these two cases, omega 0.5, omega 0.6, how nice they match the Thomas Fermi approximation method. So what surprised us that all this, it's well known that Thomas Fermi is a good approximation for big interaction, but it's not so easy. It was not so easy for us to understand that it could also predict this breakup so well and make so well these nice contours, predict these nice contours within this approximation. So here is another case, is the other case for bigger G. It corresponds in this figure to the triangles here. So here is predicted the breakup around 0.7. So, and note that there is a large difference in magnitude from here to here. And if we see omega 0.7, we have this figure. Here are the vortices, and here are the phase. Look at it in the phase. At each point, when you have a vortex, you have an inconsistency of phase. This is that well characterized. So a vortex is not exactly a place where you don't have density. A vortex is a place where you don't have density, but also you have inconsistency of phase. It's meaning that you have around this point, you have all phases. If you go around this point, you have a variation of phase from minus pi, or from 0 to pi. You have a 2 pi variation around. If you walk around any of these points that correspond to the vortices, you have. So this is really characterized a vortex, not exactly a point where you don't have density. But of course, when you when you have inconsistency of phase, the only way that nature can be fixed is to give 0 density. Then when you have some wave function psi equal rho multiplied by exponential to some phase, the only way you can satisfy having all kinds of phase, that you have density of 0. So when you increase from 0.7 to 0.77, you have exactly the breakup as predicted, and the contour also from Thomas Fermi The prediction was from Thomas Fermi approximation was 0.764, and we obtained here clear agreement, very well agreement with the theory. So we analyzed also the R-quartic confinement. In this case, we have here R to the power of 4. If we calculate using the Thomas Fermi approximation, it's more complicated. I will not present everything here, but in fact, I will not present the numerics, the analytical calculation, but I can tell you that at some critical velocity, you have a giant vortex. You can analytically do that. And at critical velocity, you have breakup. So in the same way, we also performed these studies along some parameters from GB to the power of 4. And we analyzed also the case 0 and 0.5. So if you start in this position and start to go up from here, if you increase rotation, what happens? You have a formation of giant vortex here, and then if you go up through this line around GB to the 4, around 16, if you go up, finally you have a breakup. So I can show you. This is GB to the power of 4 equal 0.2, and what you have is, this is Thomas Fermi, the density predicted by Thomas Fermi. Before I just showed you contours, now I show you also the density. And here is the GP full numerics, and exactly as predicted, you have a breakup here. And so this is the case, this is the case, in fact, I showed this case for GB equal 0.02. I showed this case. Now I show you that case, and showing that case, it's, as I said, as I increase the velocity, first it appears a giant vortex, and then finally you have a breakup, not exactly as the other one, but now it splits here along this line, along pi over 2, theta equal pi over 2, it splits. And here the parameters are for A equals 0. This is also a very nice picture. Then we increased the G, and then we obtained more vortices in this case. And exactly, it broke up in that diagram. So conclusions of this first part: breakup can be achieved in rotating non-dipolar quantum gases in asymmetric quadratic traps under X or R quartic confinement. And Thomas Fermi approximation can be well applied in these asymmetric cases with remarkable agreement. And within Thomas Fermi approximation, analytical solution for critical rotations can be obtained for giant vortex and breakup. This is in PRA 2020. Okay. Now let's go to the second part of the talk, this stability of Bose condensed mixture on a bubble trap. First, we have motivation, a main equation, stability analysis, time-dependent evolution, and finally, conclusions. Even from the beginning, there have been exploration of BEC in different geometries, maybe in cigar shapes, in pancake traps, so many different geometries. A long-standing possibility is the shell geometry realized in a bubble trap. So you confine your condensate on a bubble. Okay, you confine on a skin of a bubble. So bubble trap is inaccessible on Earth due to gravity. So they send, a possibility is to do this experiment in NASA Code Laboratory at International Space Station. So this is a BEC that they packed everything and sent to space to the International Space Station. And it's possible to do this in this microgravity environment. It's possible to make this, this bubble trap. These are references about this, and several works on bubble condensates appear recently. There is one from Tononia Salashnik, Bose condensation on first surface of a sphere. There is Pristipino and Giacchina, ground state of weakly repulsive soft star bosons on a sphere. There is from São Carlos here, from Monica that's here at my side, and Bagnato, and Lucas also here. Beretta, I don't know if Beretta is here. Hi, how are you? And another work is from Diniz, Oliveira, Lima, and Emmanuel Rein. I think all of them are here too. And there is other works from Padavich, this Sun, Lanetan, Visheva, vortex, anti-vortex physics in the shell-shaped condensates, also 2020. Avelin et al., observation of Bose-Einstein condensate. This now is experimental work, Nature, London, that they finally did this condensate on Earth. And Corolla, observation of ultra-cold atomic bubbles in orbital microgravity. So it's a theme that a lot of people are interested now, and I consider it a hot topic. So bubble condensates, it's in a good wave now. So we have experience in some mixtures, and we looked at, during our journal club, it was happening because of our journal club, one of us, I didn't remember which one, maybe I myself or the shoe, someone selected this work, previous work on mixtures on a ring geometry. So they discussed how will be mixtures in a ring geometry, and immediately came to us the idea, so how it will be in this bubble sphere, the bubble trap, how it will be a bubble condensate in this system, how it will be. So looking to ideas of this paper about the miscibility, we make a similar model to them, but now this is, of course, in 2 dimensions, in the dimension theta and phi in the sphere. Since there are 2 condensates, in fact, we have 2 coupled condensates here, and these 2 coupled, of course, you are not seeing, if you look at the Laplacian, it doesn't contain the R term in spherical, because the R term we are neglecting. There are some analyses in our work that this skin, this delta, should be around much smaller than 8 pi square over the interactions. And if you consider this distance in units, in length units of R, very small. So if you have a very small skin, you can neglect also this the term in R. So we just did, it's a very simple model. It looks not so simple because they are coupled equations. In fact, not simple to solve numerically, but it's much simplified that if you have the real 3D problem. So we are neglecting the variation. We are considering that the density is around the skin is almost constant, or is in terms of energy contribution in these equations is irrelevant. So we have these 2 coupled equations. Gamma 1,1 is the self-interaction. It's like the G in the Randy Hewlett 1D he was explaining, is the interaction, self-interaction. Here is the interaction between one species and second species. And here is the self-interaction of the second species. And here, gamma 1,2 is equal to gamma 2,1 is the interaction of 2 with 1, the magnitude of 2 with 1. We consider here the symmetric case, so the number of particles in both species are the same. And we consider that the species also have the same mass. So it's more it's feasible easier in the case you have, for instance, rubidium atoms in two different hyperfine levels. So since then it's equivalent to have two species. And let's continue. So you have these coupled equations. We can have these solutions with azimuthal symmetry. So you think in a sphere, and you have from the South Pole to the North Pole, you have the azimuthal symmetry in this direction. So it's symmetric to rotations to phi directions, And here you can consider quantum numbers s equals 0, minus and plus 1, because it's the s equals 0, you are considering a homogeneous mixture. You have one species homogeneous distributed, the other species homogeneous distributed, and s equal minus or plus 1, you consider from one species you have a vortex and a vortex in the North Pole and an anti-vortex in the South Pole. It's like the Padavich paper. And these are the solutions you have. And on top of the solutions, you can analyze the stability of the solutions. So what you do, you make a linear perturbation theory that you add some perturbations here, and these perturbations, this is a standard procedure. You add this perturbation expanded in angular momentum modes. And this is well known as the Bogoliubov-de Gennes perturbation theory. So if you insert in the model the equations, we get the Bogoliubov-de Gennes equations. These equations for the perturbation, in fact, U is a perturbation, and you build up on those ground states, you build up this matrix form. You have this, for two species, it's quite involved to build this matrix. Numerically, it's quite tricky. But we had experience with other works we did before. And this is what does it mean, these D's in this equation. So this is this operator, you must put in this operator. So when you apply to this matrix to this system, you can diagonalize it, obtain the eigenvalues and the eigenvectors. So the eigenvalues are these frequencies. So whenever this frequency is imaginary, the system is unstable. It corresponds like when you have an harmonic trap with negative frequency or with imaginary frequency, it corresponds to unstable case. So imagine you have a mountain, you put a ball on top. Any perturbation can make this ball go up. But if you have a trap, a well-known harmonic trap, for instance, or a ball in a well, it will be stable there. So imaginary frequencies means instability. So we calculated this and obtained from these imaginary eigenvalues, we could obtain a stability diagram that I will show in a minute. For the case, in the simpler case with S1 and S2 equals 0, there is no vortex. No vortex in North Pole and the South Pole, and BDG is simple and then can be computed analytically through spherical harmonics. So indeed, you can compute it analytically, and you have this frequency equal to this result, and omega equals 0. If you do it, you can simplify gamma 1,1 and gamma 2,2. Then if they are equal, you remove this term, and you have a relation between you have a relation when this is stable or not. And here we show for different modes, spherical harmonic modes for different L's. So you see that for gamma 1, 2, it will be unstable. Here is the imaginary part, the frequency. When you have imaginary part, it's unstable. So from this point to going in the right direction, from about 16 going to the right direction, it's unstable. And what you have here is stable. And here we show in the figure C, we show gamma 1, 2 equal 10 is stable. If you increase gamma 1, 2 to 20 and you start up, they will find the ground state. If you calculate the ground state, it will be lower. It will be not stable in this region. And so they mix up. Here, they are immiscible. Both species are immiscible. Here, one goes to the North Pole and the other concentrate more in the South Pole. And here, when you increase the 400, it's even worse. They almost separate. One is almost concentrate North Pole and the other in the South Pole. In the case S1 equal minus S2 equal 1, it's more complicated. It's called hidden vorticity because one is like rotating in one direction and the other counter-rotating. So when you add up all the angular momentum, it should be 0, the total angular momentum of the system. Then it's much more complicated. Numerically, we can calculate all this. We can find the ground state or find not exactly the ground state or find the state of the system and compute the modes that the system gets unstable. So whenever you have imaginary part here, non-zero, the system gets unstable. Here, we build this for gamma 1, 1, gamma 2, 2 equal 10. And here, the same picture now in the other frame for equal 1, 1 and 2, 2, equal interactions, and gamma 1, 2 equals 0. So building all these figures, we can find many, many modes. And we finally get, for this system, S1 minus S2 equal 1, we have this stability diagram. So here I put this X that I show in a minute, and here this is star. So X, M equal 2 here, so it's a stable mode. It should, let's say, break in 2 parts. And here, in this set of parameters, M equal 3, so it should break in 3 parts. So the most unstable mode is M equal 3. And here is a stable region. Let's see in the stable region, gamma 1, 1 in the X case equal gamma 2, 2 equal 10. So gamma 1, 2 equal 8, it's stable, is the red dotted line. And if we increase to 12, it will get unstable. And in this particular situation, it oscillates. You can calculate the total angular momentum of each species, and you get it switches from 1 to -1. There is a strong oscillation, but note that total angular momentum is conserved. And here we show the miscibility parameter. It's defined by this form. It's the density multiplied by the other density, and quartic in the other direction. So in the beginning, they are, as we started them as miscible, and then it's lose miscibility, but it oscillates. So this is a particular case in that diagram as an example. Another example is the case is the case omega 1, 2 is 95, m equal 4, it's unstable mode. So in t equals 0, here we make a time-dependent evolution. We started them here, species 1. Here there are different views from y and z and here y and z. So here in the North Pole, there is a vortex, and here is anti-vortex. So here you are looking to the, you are looking from the North Pole in the second right column, and in the third column, you have the second species, and here you have the vortex case in the second species. So these are density plots. And as you evolve, you see that you can clearly see that it breaks in four sections. And this chemical unstable mode you can see in that diagram. So whenever you have unstable mode, you see which one, unstable modes, you see which one have the biggest omega, and imaginary omega. And this biggest omega, imaginary omega, is that will turn out to break the system in parts. So m equal 4, the most unstable mode, will make the system break in 4 parts. And now I show another example that the system, I can show you in the diagram. In the diagram is this star, and as you see, it's gamma 1, 2 is negative, and because it's negative, and gamma 1, 1 and gamma 2, 2 equal 10, so the interspecies is very negative. It can make the system collapse. The system does not sustain. And let's see what happens if we load initially them, what will happen. So let's see. Here. System is not advancing. Okay. Let's see what happens. So we make a small movie, and the left side is the density along the sphere, and in the second, in the middle one is the phase. And in the third one is looking what happens in the direction, in phi direction. In the beginning, it looks very stable, but at some point, it gets completely unstable, and it collapses, very similar to what Randy Hewlett showed you in the formation of the solitons, but here we have in a sphere. I will put the plate another time. And it breaks exactly in 3 points as the linear analysis, Bogoliubov-Degen's analysis predicted. Sorry. Not this one. No. So around 6 or 7, it should get completely unstable. And this is numerical. Numerically, these numerical fluctuations make the survival of these unstable modes. And as I told you, the m equal 3 is the most unstable one, and the system collapses. So there are three points of where the system collapses and this formation of these spikes. Of course, if you really do these experiments, if you really do, in our calculations, what happens is that our numerical codes break, but if you do the experiments, you have, when you have too much density on some points, you have 3 body losses. And these 3 body losses will limit the density that can happen. We haven't done any calculation with 3 body losses. We just predicted the unstable modes. There is another work that appeared recently on dual species mixtures. They are considering their rubidium and lithium, if I remember, yes, the rubidium and lithium, and they are considering mixtures there in a different scheme. They are doing different considerations from us, but it's also interesting. Conclusions, homogeneous mixtures in bubble can turn unstable depending on inter- and interspecies interaction. In bubble confined geometry, critical point of stability, G12, it's well known that in homogeneous infinite system, G12 must be less or equal to G1, square root of G11, G22 to be stable. But if you do in this geometry, it's extended in this simple calculation of omega. You can show it a very simple expression. As in the work of Malamed and collaborators, it's, the stability is extended. And unstable modes can be analyzed by Bogoliubov-de Gens, and time evolution confirmed all the results. And this is in PRA 2001. So I thank the organizer another time for the invitation.
Thank you very much, Arnaldo. Now we'll have time for a few questions. Please, please come on. Yes, please. Você pode falar aqui no microfone. Pode chegar bem pertinho.
Hi, can you, okay. So during the presentation, if I remember well, you show us the phase profile and the density profile. And if I understand well, that you calculated the density profile from the phase.
Which slide are you talking?
In the first part.
The first part?
Yeah. Here. So you found the density profile using the phase? Or?
No, we do numerically. We make two kinds of calculation. We propagated imaginary time. We make imaginary time calculation to find the ground state, and once we have the ground state, then we plotted the density and the phase. So what we calculate is the psi. We calculate psi.
Okay.
And from psi, we extract the density, making psi square, and from the phase, we make some arctangent of the wave function, something like that.
So here is the theoretical simulation, right? Or
everything is theoretical. There's
so, yeah.
no experiment here.
So does the method work well if I introduce some random noise along with the signal?
Usually those solutions are robust against noise.
Okay.
They are very robust against noise.
Mm-hmm.
So I don't think they are unstable here. They are not unstable. There is no, in here, the scattering length is positive in these calculations. It's very well in the direction of the experiments, how they are done. So I don't see here any unstable mode. In principle, we can propagate in real time, if it's in real time, if it gets unstable, but I don't remember if you guys, Alex and Leonardo, I don't think they have performed time-dependent calculations to see if it gets unstable. But I don't see any reason for this to be unstable.
Okay, fine, thanks.
Okay.
More questions? No more? Oh, please, Lorenzo.
So, thank you for the great talk and beautiful result. Actually, I'm very curious about, this might be a very trivial question, but about the vortexes. What controls how many small, I know that is not the kind of the work that you showed us, but can you, by curiosity, tell me, what controls the number, or better, the distance of the vortexes when you...
The number of vortices.
Yeah, if this makes sense, I mean.
Well, in our paper we have a study about this. There's a Feynman rule, but Feynman rule is well designed to work in very homogeneous system. Feynman devised that if you rotate a cylinder, you generate a number of vortices. But here is very irregular. So you can apply some locally you can apply, and we obtained some sensible results about the prediction of the number of vortices. But of course, is not so clear as Feynman thought, because it's very irregular. So it's not so easy to predict exactly how many vortices. Of course, it will be nice if you have a general theory about that. Given the potential, given the rotation velocity, okay, give me how many vortices you have. But as long as I know, there is no complete study about this. We just have some study about how it performs under Feynman rule, and you have to adapt it. Some places there are more density, it's quite, you have to analyze when you count vortices and when you don't count vortices, because you see in this region, for instance, in this region, you still, let's see if I can, well, I cannot go with my mouse, it's flickering, but I can go with this one. So you see in this point outside you have almost zero density, and you say, oh, I count this vortex or I count not. That's a hard question to answer. If you count, so we didn't count these vortices that are in very low density. We counted only the vortices that are in let's say, in considerable density, and it agrees with the Feynman formula.
Okay, thank you. So, not yet an elegant solution of the Thomas Fermi, which works extremely well.
Yeah, we are still astonished that it worked so well in so stretched system, in so different potential, because there's Thomas Fermi in very regular cases. It's well known, but we are really surprised, and we can predict analytically the exact point within Thomas Fermi. Of course, you must have G very big, otherwise, for instance, for G equals 0, of course, you cannot use Thomas Fermi. It's stupidity to use. So it's believed that, as we didn't do this study, but it's believed that as you go smaller and smaller G's, you will lose all this prediction from Thomas Fermi. So the reason why we did with big G's, G500, G2000, but they are very well within experiments, these G's.
Thank you. Very nice.
More questions? Please, Under.
Here you go. Now I am afraid.
You want the microphone to this side?
Gammal, very nice talk. Now, you have a very ideal situation. When you divide, you have the same number of vortices in both. So I have two questions. One is, if I start to approach them, so if I could make the barrier to come down by decreasing whatever is the barrier, will vortices tunnel from one to the other condensate?
I don't think so. I think you go backwards from omega 0.77 to 0.7. I think you go backwards.
And the second one is, suppose in real life, I'm going to do this experiment. Probably I'm going to have a different number of vortices.
Probably.
Probably.
Probably. Experiments.
So suppose I separate them and wait then evolve in time. And then I let them combine. Because they have different vortices, probably their phase will evolve a little different.
Uh-huh.
And what's happened then? I know that you haven't done, but what do you think would happen?
Maybe you have interference. Maybe you have something like Ketterle original experiment.
Reconstruct the original condensate?
That's a very good question.
Okay.
Maybe they not, maybe not.
If the tunnel
Okay, thank you. Arnaldo, now we have some online questions. The first one is from Abel Beredi. They have two questions. The first one is about the first part of your talk. He says, in the full DPN numerics, I saw that the vortex are not symmetric with respect to reflection about the x-axis. Saw five-fold symmetry occasionally. What breaks this symmetry?
Let's see. That's probably in that one. Even this one is not completely symmetric in the top in reflection to the y equals 0 axis is not exactly symmetric. Well, this is numerics and how to find the ground state. Numerically, to find the ground state of the system is very tricky, and there is some fluctuations that can, there is round-off errors, so it's not a perfect, it's not so easy to find the ground state, or even if there are degenerate states, there is uncontrollable. So maybe we also have this state, and the other one, that's the image, the reflection image with respect to the y axis, to the y equals 0 axis. Maybe we have also this, it's possible also this system. So we don't have a full control if there are degenerate, or if this is the exact ground state of the system. But we can follow and we see the energy going down, down, down. So we do with many simulations. We start with different initial conditions in imaginary time or either in Newton conjugate gradient methods. Start with different conditions, and they usually go to this or very similar to these shapes we get. So I cannot fully guarantee that this is the ground state. If it's not, it's very close. And as you can see, it agrees, the contour agrees perfectly with the Thomas Fermi approximation. So that's the answer. There is no guarantee that it's completely the exact solution. Maybe it is, or it's if it's not, it's very, very close as we follow the energy going down and down in the propagation.
Okay, Arnaldo, thank you. He has another question for the second part of your talk. He asks, it has been shown that RF dressed traps only works for rubidium-87 mixtures due to the similarity between singlet and triplet scattering lengths. You also show the extra source of instability. What does this mean for the future of F-dressed mixture experiments?
Can you repeat the beginning?
What you can say about the meaning of, what the instability means for the future of FF-dressed mixture experiments? This instability that you...
What's it mean?
RF radio frequency.
I see. Radio frequency.
Dressed mixtures.
Well, I'm not sure.
Radio frequency traps, bubble traps.
I don't see if I understand fully the question. I know that he wants to know future experiments with...
Due to the instability that you show in your work, what this means for the experiments, how they can avoid such instabilities.
How they can avoid the instabilities. Well, this is a problem for the experimentalists to avoid the instabilities. We just did the numerical... I know that there have been many experiments considering mixtures. The mixtures separate, and I don't see any problem with the instability of doing mixtures. There have been mixtures, and they split depending on the parameters. So I don't see the instability. Maybe he sent me the paper, and I can better reply him about these questions of instabilities.
Okay, maybe they are trying also to guide you to the field, because you used in your work this different hyperfine state of the same species. But for example, if you use different masses, different species, this stability will change too much?
Well, this we must ask to our friends that just published this work. We have not studied that with different masses. We prefer to study first the easiest thing to experimentalists to do, because it's much easier to do one species. I followed, I stayed for a short time in Randy Hewlett lab, and I see how much harder it is, because then you must dominate how to trap two different species, and you have two different level schemes, different lasers, and you must, it's much more complicated and if you do mixtures in the bubble, so this is even in the space, it's even much more complicated. So I think this is much harder to do. So this is why we started studying this case, and we were preparing to study mixture, but as I see, it's more complicated, and for mixture, different mixtures, with Kishore Kumar, we studied something like that, and sometimes one species go inside and the other species go outside, because different masses, now we cannot guarantee that in the surface exactly, maybe one species goes on top and the other goes in the lower, let's say, shape of in the lower shell. So maybe if you have different masses, one goes surrounding the other. And then they naturally are already split. Before you start everything, they are naturally split because of the trapping system. So I don't know what happens. I think it's a much more involved problem and harder to do. So we did a simpler case.
Okay, Arnaldo. One last question. It's very nice that the public, online public, is also participate. We strongly recommend you to do this. And this question is from Jacopo D'Alberto. Just want to know if there are any kind of quantum Monte Carlo results about the mixture on bubble traps, if you know, if you have one.
No, I'm not aware about bubble Monte Carlo traps in mixtures. As long as I know, Salashnik did it for prediction of the temperature of condensation if just one species. I'm not aware anyone has tried to do mixture. Maybe Salashnik they are trying to do. I don't know.
Okay. Thank you very much, Arnaldo.
You're welcome.
Let's thank you, our speaker again. Okay, our next speaker will be Victor Dodonov. Please, Victor.
You're welcome.
Isso, onde posso colocar aqui?
Se quiser ligar só na hora,
Hello? Yeah. Let's continue, please. So the next speaker, Professor Viktor Dodonov, he started his career back in Russia, where he finished his PhD in theoretical physics in Moscow, 1976. Then he moved to Brazil, and now he is currently a professor, full professor in Physics Institute at University of Brasilia, UNB, where he's also a director of the Centro Internacional de Física. I don't know if there's a translation yet. So over his career, he has published over 240 papers, 23 book chapters, and a book over many other specialized literature. He works in topics related to quantum physics, mainly the dynamical Casimir effect, cavity electrodynamics, uncertainty relationships, relations, non-classical states, time-dependent open quantum system, Wigner function, phase space quantum theory, just to mention a few. And today he will speak about this orbital magnetism in a single charge, which has been known for over 100 years. Please, Professor, be welcome.
Thank you very much. Works? Thank you very much for the presentation. My talk a little bit tangential to the mainstream of this event, because I shall not tell you anything about quantum fluids. I shall tell you about quantum mechanics of a single particle. But I want to show you that this area is still alive, as quantum mechanics itself. And there are several interesting problems that were not solved until now. Therefore, I guess that for school, with some young people, it can be interesting. Maybe somebody will work in these directions. Okay, let us start. So the title is Orbital Magnetism of a Single Charge 100 years later. But later of what? So let us move. 100 years after, you see date, December 1921, when it was published the famous paper by Mademoiselle Hendrika van Leeuwen, entitled clear, Problème de la théorie électronique du magnétisme. And now results of this paper are known as Bohr-van Leeuwen theorem. Here there are photos taken from internet when they were very nice young people, more or less like you. And what is this Bohr-van Leeuwen theorem? We know that magnetism is a very amazing thing, which attracted attention of many people, including physicists, for centuries or decades. And one of the problems was the following. We know that there are paramagnetic materials, diamagnetic materials. And diamagnetic materials show this diamagnetic coefficient very small at usual equilibrium conditions. Therefore, the question was why it is so small. And the first answer, actually qualitative, not quantitative, was given by Niels Bohr in his PhD thesis. It is interesting that these two results, Bohr-van Leeuwen theorem, they were results of their PhD thesis of Niels Bohr and Miss van Leeuwen. The thesis of Niels Bohr were made in 1911. And it is interesting that now we can find practically everything in internet, because I knew about his results during decades since I was a student at university, but I never read them. Only recently I found on the internet, we can see there is some original in Danish, but it was translated. Now everybody can find this. And what was his explanation of very tiny magnetism of metals? You see, there are two pictures. The left one I take from the book of Rudolf Peierls. This is original picture from the thesis of Niels Bohr. You see, look here. It seems obvious that materials must be diamagnetic if we do not know about spin or neglect spin. Because if we have charged particle in magnetic field, then it will rotate by circle, and we know that the current will produce magnetic moment exactly opposite to magnetic field. It must be diamagnetism. Then why there is very small diamagnetism in real materials? And the answer of Bohr was the following, that in real materials we have boundaries. We do not have completely free particles. We have boundaries. And he showed, for this picture, there are these circular trajectories, but some of particles will will meet this boundary. And you see, they will be reflected. And the reflected current will be in opposite direction. And he wrote that this opposite current, we can see here, will totally compensate internal currents. But he did not calculate this. There were only words in his thesis. There are many words. I shall not read everything. Only conclusions, very interesting. You see, one conclusion. Thus, we have seen that a piece of metal in electric and thermal equilibrium will not possess any magnetic properties, whatever due to the presence of free electrons. That in the thermodynamic equilibrium, if we believe in classical physics, and this was 1911, magnetism cannot exist. And the end of his thesis was, it does not seem possible at the present stage of development of the electron theory to explain the magnetic properties of bodies from this theory. And probably this was one of stimulus why he moved to Manchester to work with Rutherford, and after that, 2 years ago, he created the first model of atom, because he was not satisfied with magnetic properties. Instead, although later it seems that he never returned to this problem. And now, what was contribution of Mademoiselle van Leeuwen? This is page of her paper. Actually, her thesis was defended in 1919. Her supervisor was Lawrence. Therefore, this work immediately became very famous, popular. All great physicists knew about this. Ehrenfest, Einstein, many others. But the paper was published in 21. And you see this most important part of this paper, this zero. Zero is for some integral which gives the magnetization of the material. So in classical physics, magnetism, equilibrium magnetism cannot exist. And how to explain this? It was written in the paper, but I wrote everything in most modern terms. We know that in the equilibrium state, everything can be calculated if we know the partition function. And in classical physics, since the papers by Boltzmann, Gibbs, we know what is partition function. We take energy in the form of Hamiltonian, put this exponential, and we must integrate over all phase space. When we calculate this, after that we can differentiate with respect to different parameters, differentiate with respect to temperature, we shall obtain specific heat, differentiate with respect to magnetic field, we shall obtain magnetization. Okay. But the important thing is that how magnetic field enters the theory, both in classical and quantum physics. The enters is well known since the time of Hamilton, that we should replace momentum, P, by the extended momentum or extended derivative, pi minus vector potential. I write everything in Gaussian system of units. And then what will happen? We have integral with respect to P with respect to Q. And when we integrate with respect to P, then we can make change of variables. Integral is in momentum space from minus infinity to plus infinity. Then we can replace this combination P minus some function of x, but another variable, and vector potential, call any function, will disappear. Therefore, partition function doesn't depend on magnetic field. After that, you can differentiate how many times you wish, but you will obtain only 0. This was a result of van Leeuwen. But we know that magnetism exists. Therefore, how to save magnetism? One more remark. You see that formally in this derivation, there is no boundary, because ideas of Bohr that magnetism disappear because of boundaries. Where are boundaries here? They appear implicitly, because after integration over P, we have to integrate over coordinate, and the integral must exist. If we have no boundary, motion will be infinite, and the integral will not exist. Therefore, boundary here is implicitly. Now, we know what to do, how to save magnetism. And now we know quite well there are two things. First, forget about classical trajectories. In quantum world, they do not exist. And take into account the discreteness of energy spectrum. Therefore, instead of integral, you have to calculate sum. Sum with exponential, with energy levels, and some factor G. This means degeneracy, because many levels, there are sometimes many states with the same energy. Okay? Therefore, the problem is to calculate these energy levels and calculate these sums. And how to find these energy levels? This problem was solved for the first time by Russian physicist Vladimir Fock. Everybody knows the name Fock states. This is the same Fock. And his photo when he was young, more or less at that period of time, and the photo when he was more old. And what he did? He wrote that Hamiltonian. He added some confining parabolic potential and solved the equation in polar coordinates using the calibration of magnetic field, the name symmetrical or circular calibration. Later I shall return to this point. Therefore, actually, you know, the solution for harmonic oscillator alone was done by Schrödinger in one of his first papers in 26, and Fock generalized it. Therefore, he obtained functions and obtained spectrum. And spectrum, you see, very nice. It has a linear dependence on two quantum numbers, because we have two dimensions, two quantum numbers. But he stopped here. I do not know why he did not calculate statistical sum. Maybe he was not interested in this topic. No, see, I did not find any answer to this question. Who obtained the solution? We know it was 2 years later. You see, this was paper submitted in January 28. 2 years and a half later, solution was given by Lev Landau. And here also two papers. When he was young, this photo, he was more or less 20 years old, and a photo when he was more or less 50 years old. And how he solved the problem? He used, first thing, he used another calibration of vector potential. Calibration when vector potential has only one non-zero component. And we know that in this case, the Schrödinger equation, here written here, can be solved if we make some trick that the wave function can be a product of wave function of free motion in one direction, plane wave, and some function in perpendicular direction. And solution in perpendicular direction is solutions to harmonic oscillator problem. Consequently, immediately we have this famous formula Landau spectrum that energy quantized, if we forget about motion in the perpendicular direction, energy is quantized. But the problem is here, that you see a wave function contains some extra parameter sigma, it was in his paper. Now we understand this is momentum in the x direction. And the wave function contains this parameter, energy doesn't. Therefore, the degeneracy of Landau levels is infinite. So how to obtain a reasonable result? And Landau obtained it. To see how he moved this, we have to look at classical equations of motion, very simple, see? Second derivative, first derivative. If we integrate, then immediately we obtain two intervals of motion, xc, yc. This is nothing but the coordinates of the center of the circle along which particle rotates. And important point in his representation that general vector potential can be written in this form, and some combinations of x and y. And we see this parameter alpha. Fock used parameter alpha equal to 0. Therefore, he solved the equation in the polar coordinates. Okay? But that solution did not permit us to see immediately how to get rid of infinite degeneracy. Here, if we take alpha equal to 1, then we see that, for instance, alpha minus will be 0. And coordinate in the epsilon direction, coordinate of the center in the epsilon direction, is nothing more than momentum in the x direction. And then simple things. As usual, when we have some free motion, we remember that no, free motion must be in some finite volume. Therefore, let us think that the particle is inside some rectangle, and this free motion along the x, and this oscillatory motion along the y-axis. But we know that in this case, we impose some boundary conditions. And frequently, we used periodic boundary conditions. And then we know that spacing between quantized momentum in the x direction is Planck constant divided by the length in this direction. This is spacing. And now we see that on the other hand, this px divided by m omega, omega is cyclotron frequency, must be limited because the center of orbit now can go out this rectangle, okay? And then immediately we can calculate how many states we have to take into account. All this extension, okay, divide by this spacing. And we obtain this formula, this degeneracy is area, and then frequency, constant, mass and Planck constant. This was the second great result of Landau. So we have to take this quantity and multiply by statistical sum of harmonic oscillator, which everybody knows. Then we can obtain this formula for statistical sum, And after that, we know that this is taking logarithm, we obtain free energy, then we differentiate free energy with respect to field, and we shall obtain this famous formula for the magnetization. But Landau did not receive this formula. He calculated another thing. I shall show you a little bit later. But this can be done. Who really did this, who arrived at this expression, was another physicist. And here only some numbers to have ideas. If we have magnetic field of the order of 1 Tesla, then the frequency of rotation for electrons 10 to 11 second minus 1. And temperature 1 Kelvin corresponds to the ratio H omega over kT or beta, about 1. So we shall have this in mind. And who obtained the complete solution was Darwin, Charles Darwin, but Charles Galton Darwin. He was grandson of another Darwin, who everybody knows. And remember, it was Landau made this work when he was in Cambridge in 1930, and he sent the paper to journal in July. And Darwin worked in Cambridge at that time, therefore he knew well the work of Landau, but he was not quite satisfied with this explanation by Landau, this additional quantization of momentum. Therefore, he wrote it. Let us consider some model when we can calculate everything exactly, and after that we shall take a limit when frequency of this harmonic trap will go to 0 or will be very small. Therefore, he actually repeated, he calculated independently the same spectrum that was done by Fock. Probably he did not know about the work of Fock. Okay, he did not cite him, but he obtained this result. Okay? So we see how diamagnetism appears in quantum physics. And now I want to show you some interesting things in this respect. I will show how it could be done before, first thing that Fock did not do this. But even before Fock, it could be done, not in 30, not in 31, but in 27. How? And you see that how we calculate, and some words about work of Landau. He was interested about properties of metals. Therefore, of course, he took into account Fermi statistics. Therefore, he calculated this Gibbs potential, and he made much more complicated calculations. And making calculations, he calculated orbital magnetic moment compared with Pauli spin magnetic moment. And he wrote that diamagnetism 3 times smaller than paramagnetism. This was a result by Landau in that paper. Now, how we can calculate in a more simple way? This is statistical sum. What is this sum? This is nothing but the trace of things which we know as statistical operator. Here's exponential of Hamiltonian multiplied by this inverse temperature. And now let us look at another operator named evolution operator, also exponential of Hamiltonian, but multiplied not by beta, but minus ET on the t time. And we see that there is simple relation. If we know evolution operator, then if we change real time by imaginary quantity, we shall obtain this equilibrium statistical operator. Now it is obvious for everybody, but it was not obvious at that time. And now, okay, so problem is, let us try to calculate evolution operator. And then we see, then knowing evolution operator, we shall obtain matrix elements of this operator, which we call now density matrix. And it was introduced by Landau in one of his first papers in 27. when he was 19 years old. And how to calculate this evolution operator or its matrix element, which named propagator, because it moves initial wave function to the function at its instant t. And now, how to calculate propagator? Of course, if we know complete system of solutions, then we have to calculate this sum. And in this way, it was calculated the first years of quantum mechanics by somebody, but this is a complicated way. There is a much more simple way. What is? Suppose we know operator x capital for x small, this one, Ux, U minus 1, and the same thing for operator p. Then we can rewrite this definition in this form, that operator x capital applied to U from the left. This is the same thing that U multiplied by x small at the right. Now let us rewrite this in form of matrix elements. We obtain equation where you see x, operator x acts on the g as function of the first variable. The second variable here fixed. And the result is the same function with coefficient x prime. Therefore, propagator is eigenfunction of operator x. And for p, similar things, but p is the derivative. Therefore, here we shall apply an operator p to the left, and here will be derivative with respect to second variable. Okay? It is much more simple problem. No summation, only problem of solving simple differential equation, provided we know these operators. But when we know, and there are simple cases when we know from the beginning, almost from the beginning, what cases? We can immediately see that this operator, x and or p or another one of this structure, satisfies this equation. But this is equation for quantum integrals of motion. If everything doesn't depend on time, then we see that Hamiltonian commutes with this operator. This means this integrals of motion. This is more general situation when operators depend on time explicitly. Therefore, we have to find integral of motion which consigned with x and p at the initial instant of time. In general, the problem is very complicated, practically impossible to find them independently. But for many systems, when they describe a quadratic Hamiltonians, free particle oscillator, particle magnetic field, the chains of oscillators, Hamiltonian is quadratic. Then equations of motion are linear. Therefore, we can see immediately that these integrals, big letters p and x, are related to small letters by means of some matrix lambda, depends on time. And we can easily show that equation for this lambda is very simple, very nice. Derivative of this lambda is the same matrix. Matrix sigma is matrix of commutators between x and p. And this matrix B, symmetrical matrix, which determines our Hamiltonian. And in the stationary case, solution immediate. Then we have to calculate exponential of this matrix. And calculate exponential of matrices, very nice problem. Everybody knows how to resolve it. Therefore, this can be done. And it was done by Kennard in 27. He used exactly this method and calculated propagator for harmonic oscillator, for particle magnetic field, for particle in electric field, using this approach. And actually, this paper is very, very nice, very important. He was the first person who proved exactly the uncertainty relation by Heisenberg. We remember that Heisenberg did not prove. He made some thoughts and told that product delta x per delta p must be not smaller than something of the order of Planck constant. But Kennard proved this exactly. He proved this when he was in Niels Bohr Institute in Copenhagen, and paper is very nice, but it was forgotten, almost forgotten, for almost 50 years. It seems to me that Niels Bohr did not understand this paper because he never made some propaganda with this result. Because we know that now it is very popular to work with squeezed states when some variance is much smaller than vacuum value. They were introduced here in this remarkable paper by Kennard. But sometimes life is very funny. And now we can see, he calculated propagator, and now the immediate step, change t by minus e Planck constant beta. Why he did not do this? From my point of view, the answer is because he did not know about the statistical operator. Because let us look. This paper was submitted on July 17, 27. And the paper by Landau, where he introduced density matrix, was submitted 10 days later. Therefore, Kennard did not know about this. And who did this for the first time? It almost more than 20 years later. It was done by Sondheimer and Wilson in 1951. They calculated the density matrix, this is psi, not a wave function, by density matrix, using method much more complicated than method of Kennard, but they calculated in this way. And after that, of course, they obtained statistical sum and everything. Really, the most simple way is to use Wigner function, because Wigner function is very symmetric with respect to P and Q. And if we use Wigner function, we can calculate it for most general quadratic system. It contains two terms, one exponential, okay, quadratic form, and then again some function of matrix, B multiplied by sigma. After that, we can calculate statistical sum and many consequences. But in reality, this was done only in 82 by our team in Lebedev Institute in Moscow. Okay, this is the history, some special case how to calculate for the magnetic field when Hamiltonian is specific, one matrix of masses, and this matrix can be complicated when we have different masses in different directions, some anisotropy. But everything is reduced to calculation of some determinant of related matrix. Okay? And one more thing which I want to show you, the following. Landau calculated everything for degenerate gas, which obey Fermi-Dirac statistics. How it can be done without terrible calculation made by Landau in 30? We see that in Fermi statistics, we have Gibbs potential, that logarithm, okay, and one particle density matrix. This is nothing but Fermi or Bose distribution. And great result was the following. If you know statistical sum, Boltzmann statistical sum, non-degenerate, then Gibbs potential can be obtained by inverse Laplace transform of this sum. And one-dimensional operator also can be obtained by non-degenerate statistical operator multiplied by some kernel and inverse Laplace transform. This was done by another great Russian physicist, Yuri Rumer, in one of papers in 1988. Now here again, his photo when he was young, of your age, and the photo when he was much more old. And how can be done? You see, very nice figure in how calculate this omega potential, this inverse Laplace transform. Inverse Laplace transform is made over the vertical line in complex plane. And we know that when we calculate something in complex plane, we can replace this vertical line by another contour, and each has a circular path, and this cut, because in 3 dimensions, there appears some square root. If we have some square root, then we have to make cut. And what appears here? Integral along this cut is nothing but mean magnetization calculated by Landau. Here we have many poles due to the sine function in denominator. And these poles give famous de Haas-Van Alphen oscillations. And we know that Landau, in his first paper, he wrote that probably there exist excidations, but he wrote that experimental skill cannot determine it. But it was determined, discovered a few years later. He had to write another paper. Okay. So these old results. And now I want to show you some new results and attract your attention to problems which still can be resolved. A few years ago, I and my son, Alexandre, thought about the following question. Why this diamagnetism is so small? Okay? I repeat these formulas, and we see that it is small. And one of the answers is the following. Of course, this is small because in classical physics, it is 0. So if we introduce quantum mechanics, we shall obtain small corrections. But suppose that we do not know about classical physics. What do we know? That at 0 temperature, we have great magnetism. When we increase temperature, magnetism becomes smaller and smaller. Why this happens? And one answer can be named thermodynamical, because I showed you already that mean value of magnetic moment is derivative not of energy. This derivative appears only at 0 temperature when we have no external world. At finite temperature, everything which appears is free energy. And this is the difference between total energy and entropy multiplied by epsilon temperature. But for high temperatures, this entropy term will almost eliminate energy. And this will give us small magnetization. But we can think in another direction. You see, magnetic moment is some observable. And we know in quantum mechanics that each observable has some operator. And mean values can be obtained how? To multiply, apply this operator to psi function, multiply by psi star, and integrate. Or in general case, apply to statistical operator and calculate trace. And question, what is the magnetic moment operator? How to obtain it? And we can start from the classical famous formula for the magnetic operator. You see that simple formulas what? That magnetic moment is current multiplied by area inside the trajectory and some coefficient. Okay? But if we have distributed current, then it's this three-dimensional integral where density of current appears. But what is density of current in quantum mechanics? Everybody knows that this is product of psi by gradient of psi, but in magnetic field, some extra term appears here. And if we put this expression in this, we immediately can obtain the standard formula, psi star, then something, and then psi, integrate. What is this something? Something, this operator of magnetic moment. You see, this coefficient favors zero magnetic ratio, E over 2 MC, and here is angular momentum. But angular momentum not canonical, But kinetic angular momentum, here appears this pi operators, this difference between P and vector potential. So we have this form, or we can write in terms of canonical angular momentum, this appear this expression. And now what can we do? The first question, what is the spectrum, what are eigenfunctions? The spectrum, of course, continuous, okay? And what are eigenfunctions? And eigenfunctions can be found in the most simple way in the momentum representation, not in coordinate as we do frequently, but in momentum. If we write everything in momentum representation and look at this part, we immediately see that this is nothing but Bessel equation. And we immediately have solution in terms of Bessel equation and standard form exponential EM phi. But coefficient, very interesting, gamma, coefficient square root, algum parameter kappa, and this difference, m quantum number, which can be positive and negative, minus lambda, this eigenvalue, and this gamma must be real. If it will be not real, then this function will grow to infinity, and the function will not be normalized. This is a very important restriction, that lambda must be not more than m. Okay? We found this. After that, can we do? What can we do? We have to compare with eigenfunctions of energy. Again, this is problem by Fock and Darwin, this Hamiltonian, these solutions, this product, some power, Laguerre polynomial, and exponential, in this spectrum of Fock and Darwin. Now we can calculate the projection of this state, for instance, in the vacuum case, zero temperature, projection of this state on the eigenfunction with zero angular momentum, because this is vacuum state. Integral is very simple, and the result is interesting, that this will be exponential distribution. But exponential distribution only in one side. When this lambda is negative, this exponential. When lambda is positive, it will be exactly zero. And this shows us great magnetism at zero temperature. But you see what are consequences. Immediately we can calculate mean value given by this ratio. Omega g is extended frequency. It contains frequency in magnetic field, Larmor frequency, and the frequency of this trap, harmonic trap. And it appears that fluctuations are very huge. Fluctuations are the same as mean value squared. Therefore, every time in one particle, we have huge fluctuations of magnetic moment. And then, what can we do? What to do in the non-zero temperature? In non-zero temperature, of course, we have to take these projections to every state, okay, and multiply by this Boltzmann factor and calculate sum. Under this restriction, you see argument C is Q, the ratio m minus lambda. Remember that this must be non-negative. And the double sum appears that sum over quantum number, radial quantum number, can be calculated exactly, okay? And we obtain this formula, the sum over m, Pm from one side, not very complicated. This, again, Bessel function and exponential. But due to this restriction, this sum cannot be calculated analytically. We have to calculate numerically. And the convergence of this sum is very slow. And what is the result? But before the result, I will show you again fluctuation, sigma lambda. And you see that for trap with small frequency, this fluctuation diverges. Therefore, it shows that we cannot calculate fluctuations in the oval space. Every time we have to take into account the existence of boundaries or existence of some confining potential. And what is the result? Numerical calculations. You see, for different ratios of Larmor frequency omega to this confining frequency. Very interesting function. If we see parameter eta is h omega divided by kt. If this parameter big, this means low temperature. And here, parameter is taken to 10. And you see the distribution is asymmetric. If we take eta very big, then we shall arrive to that exponential function when this part will be eliminated. We shall see only this part. And the plot is in logarithmic scale. This means this is exponential distribution. But there is some fine structure near zero. And you see that here we have discontinuity. Why discontinuity? Because remember, there was sum over Bessel functions. But Bessel functions have properties that all Bessel functions are zero at zero argument, except for the Bessel functions of order zero. It is not zero when argument is zero. And this shows that when Bessel functions of zero argument enter a game, then we have this discontinuity, not very big. You see that we have some asymmetry here, and this is for high temperature case. Parameter eta 1 over 10, and we needed about 10,000 terms in the sum in order to have normalization equal to 1 with precision about 10 to minus 3. Okay? And you see what happens. Mean value of this lambda is minus 0.003. And the function is completely symmetrical. Only some fine structure nearby zero. And exactly this fine structure gives us small non-zero magnetization. And this result obtained by us some time ago, and this approximate function for that wins approximately, again, exponential function, except a very small region nearby zero. And some new results. This because something is very interesting. When we calculate either mean magnetization in high temperature regime or variance, then calculated magneton Bohr by mean value of this lambda, we see that Planck constant disappears. We have magnetic properties which do not contain Planck constant in the high temperature regime. And other results. Okay, I guess I shall skip some results. Only one, I shall tell one words. You see what is the problem with this angular momentum operator. We have a constant of motion, qual. If there is no magnetic field, then of course canonical momentum, okay, due to symmetry. If we have magnetic field, there's some generalization, and generalization will be this one. Kinetic angular momentum plus this term which contains the space extension of our wave packet. And in general, this quantity, total quantity, is conserved, okay? Then it means that this quantity, angular magnetic moment, in general case, is not conserved. So it makes some oscillations. Therefore, some problem was, are there some states when there are no time oscillations of magnetic moment? One answer is obvious. Equilibrium states, of course, then everything is fixed and does not change in time. But the problem that in many interesting situations, equilibrium state does not exist. If we have free particle magnetic field, if we remove this harmonic potential, equilibrium does not exist. Okay? And then question, are there some states when, even in this interesting case, magnetic moment does not oscillate in the stationary case? And we found these states, but I guess I can skip in details. We found some two-parameter family of states. It is interesting that in the one-dimensional case, all states are equivalent to all these invariant states are equivalent to thermal states. The only parameter is temperature. But if we have more than one dimension, then we have more parameters. In 2 dimensions, we have 2 parameter family. In 3 dimensions, 3, and so on. So we found this family of states which are invariant in time when the magnetic field is fixed. Okay? But the details, I guess, not very interesting. I shall skip this. And now, question. And now let us suppose that we can vary magnetic field. Okay, we have particle in some trap. It was in equilibrium state. And now let us change magnetic field in time. What can happen in this case? The most interesting answer appears when we change the sign of magnetic field. It was, for instance, in this direction, and we shall diminish, and then field will in opposite direction. What can happen? Then we have to solve the same system of equations. Lambda dot is lambda sigma b, but when b is function of time. And until now, there are no solutions to this problem in the general case. There are solutions, known solutions in 2 cases. One case, when we have this symmetrical gauge of vector potential, when it can be shown, it was shown 50 years ago by my teachers Ilya Malkin, Vladimir Manko, and Dmitry Trifonov, who was a PhD student in that time. They showed that if we have this symmetric calibration, then this set of 4 equations, you see that 4 equations, the matrix 4 by 4, can be reduced to the classical equation of harmonic oscillator in this case. And after that, if we solve this equation, okay, in principle, we can calculate everything. Okay. But in other cases, no. One more special case is Landau gauge. Then also we can reduce to equation of this time. But in this case, we need much more solutions. Not only this function, but 2 integrals of this function. Actually, it was my first work when I was still a student more than 50 years ago. Okay. And again, I show that everything can be written in terms of this mean energy contain this product. You see, modulus squared of this function and the magnetic field, okay, and the mean value of magnetic moment, the same things. But what can happen? We suppose that magnetic field was constant initially, then it varies, and then comes to some constant level, new constant level. Then final solution will have the follow from some frequency, okay, and 2 plane waves in the time space with positive exponent and negative exponent. And these 2 coefficients satisfy this condition. It can be easily shown. Then if we know these parameters u plus and u minus, we can calculate mean energy and mean magnetic moment. And we can see immediately that in the final state, magnetic moment will not be constant. If we take any state which is invariant in the initial state, after the evolution, it will make some time oscillations with double frequency. Okay, but what can be calculated? What can be results? And for instance, if we have very fast variation, this field, and very rapidly it changes its direction. Okay? Then these 2 coefficients, u plus and u minus, given by these formulas, and we see that if we have exact field inversion, magnetic field will be of the same magnitude but in another direction, then this U minus exactly 0. Exactly 0, but energy and magnetic moment will not be the same. Some parameters, we change their order. There are two parameters, G minus and G plus, and the coefficients will change. So in this case, energy will be the same, and magnetic moment the same by absolute value, but in another direction, in the only case, 0 temperature. If temperature is different from 0, then we change magnetic field, but the state will be different. And the most interesting result is obtained when we have very small variation, very, very small. How to come to this result? There is one special case interesting, some special case of family named Epstein-Eckert profiles. Do you see this combination of exponential, two exponential numerator and an exponential denominator? In this case, that equation can be solved exactly in terms of Gauss hypergeometric functions. And about Gauss hypergeometric functions, we know a lot of things, but not all things. But fortunately, in our problem, everything can be done exactly. And what happens in this case? Some analysis of coefficients which appear, but you see, for instance, the final energy. There is some initial energy. A final energy, this initial term, plus something. At 0 temperature, these two coefficients are equal to 1. Then the final energy will be 3 times bigger. And if temperature is not initial, not 0, the final energy will be much more bigger than the initial one after this adiabatic evolution. And there are some interesting figures. They were obtained by my PhD student, Mateusz Horowitz. He defended his PhD work in last November, okay? And we wrote several papers with him. And two plots are very interesting. Ratio of final energy to the initial one is function of final frequency. It can be positive, can be negative. And the parameters the following. With this very small number, this is adiabatic evolution. Big number is this instant jump, okay? And this figure for 0 temperature is for high temperature. And we see, in the case of adiabatic evolution, we see that for positive final frequency, we have straight line. What is it? This is well-known adiabatic invariant. We know that for harmonic oscillator, ratio of energy to frequency in the adiabatic regime is constant. And this is, we see this constant. In, coefficient is 1. But when we go to inverse, field inversion, again we see here the ratio of energy is straight line, but another coefficient. Here is coefficient 3, and here coefficient much bigger. I see how it happens in formulas, but I do not understand the physical reason why this coefficient appear. Okay? Therefore, it is some challenge for people. And one of consequences interesting, which we called giant diamagnetism. What is it? If we have the situation when trough frequency is small than initial Larmor frequency, then we can calculate this mean value of parameter lambda. After multiplication by zero magnetic ratio, we shall obtain magnetic moment. And in this approximation, a very simple formula appears. But you see, what appears in the denominator? Some parameter eta minus, eta minus difference of two quantities, eta g and eta. Eta, this h omega divided by temperature. Eta g, thing very the same nature, but frequency change by this g squared. But if g is very small, all these coefficients are very close. Therefore, difference will be very small. Therefore, we have very small denominator. And when this magnetic moment will be small, when the numerator also small, and numerator small, when this parameter q here will be close to unity. Then we have small quantity numerator, small denominator, something not very big will appear. This appears exactly in this equilibrium state. But when we change the magnetic field, especially when we change the sign, you see parameter q, omega by module squared positive, but omega changed the sign, then q will be negative. And of course, numerator will not compensate the small denominator. We shall obtain huge diamagnetism. So this is interesting result. And again, I show you that final result will be without Planck constant. And for instance, numbers. For eta 1/10, what does it mean? It means that if we take temperature about few Kelvin, already we have in high temperature regime. Okay? And you see, in the equilibrium case, we have minus 0.03. But when we invert the field, this ratio is 200. We have amplification more than 1,000 times. What is exact physical mechanism, I do not know until now. But what figures I want to show you. This figure again for the probability distribution of this magnetic moment, or this parameter lambda. This is initial state, high temperature state, the same figure that I showed you before. In logarithmic scale, you see these two straight lines, and very, very symmetric, with very, very small asymmetry here, which gives this minus 0.03. What will happen if we change the sign of field? We already know that mean value of lambda will be much more, 200. Then, how this thing will change? And I thought that, of course, it should be deformed, and probably it will move to the right, because now the mean value will be strongly positive. But what will be the change of the form? It is impossible to guess. And a few days ago, Alexandre gave me some preliminary results. And from my point of view, it is impossible to guess what will be new distribution function. Look. For some parameter, I shall not explain why we took this parameter, you see this negative part becomes very small with some oscillation for small values of lambda when the first Bessel functions appear. And after that, you see some oscillation, and after that, almost linear decay, because this is not in logarithmic scale, and this is part only to lambda equal to 60, and mean lambda is about 200, and actually, to obtain this plot, he used about 13,000 points in the sum. And here you see very, very slow decay, very slow decay. I guess that directly it again exponential in this form. And this is the result, how appears this huge diamagnetism. And now one reason is clear why this happens, because when we have time-dependent magnetic field, we have time-dependent electric field, partial derivative of vector potential over time. And this electric field will change the energy, will change magnetic moment. But what is the challenge? We have calculated this for this symmetric calibration. For any other calibration, until now, we did not succeed a result, especially in the adiabatic case. Therefore, it is challenge 100 years after the beginning of story, some things still will not resolved. one challenge and the other. I show you that problems are still open. And for instance, more realistic models of boundaries. Of course, there is harmonic potential in this model, especially when we have adiabatic evolution. You see, field goes to zero, then increases. But when the field goes to zero, this means that spatial dimension of packet will be very huge. And will be very huge, and then, of course, real boundary will appear. How to take it into account, this is a problem. I don't know whether it can be solved analytically, maybe numerically, but numerical calculation will be extremely complicated. And another very interesting thing, we know that what are real traps. One of traps is Penning trap, when we have some quadrupole electric field, okay, and magnetic field in perpendicular plane. But in this case, we have that in the plane appears parabolic potential, but with negative sign, which means that this G squared is negative. And then the problem that energy spectrum is from minus infinity to plus infinity. Then there is no equilibrium state. So probably other states which we found, the two parameter states, will enter game, but how I do not know. And what happened when omega changed the sign? In this Penning trap, which is a real object, people work with a Penning trap, but what can happen in this case, I do not know. So, sorry for time exceeded, permitted one, but I shall finish here. So I want to show you that even one particle world is still attracting. Of course, quantum fluids are much more complicated, probably much more interesting, but this area also deserves attention from my point of view, especially for young people who choose the direction of their further work. Okay, thank you very much.
Thank you, Professor Dodonov, for the nice talk. We still have time for one or two questions. Please, any questions, comments? Something on the internet? No, really. Okay. Lucas, please.
Thanks, Victor, for the lecture. Regarding that similar behavior near lambda equals 0 in all the problems that you presented, could it be an artifact of the boundary conditions or something like that?
No, of course, I have to think about artifact of boundary conditions. But it seems to me that not.
And lambda equals 0 is a perfectly valid physical situation, or is there some problem there?
Yes, this is probability density of almost zero magnetization. This can be, but so the answer can be done if we change the boundary conditions, if we take a more realistic model. Maybe, but this should be done, of course.
And if somehow you can think of a condition that excludes the lambda equals 0, the origin, then I imagine that you would have those second Bessel functions, the Neumann functions, and the things would be totally different, right?
So you suggest to remove this term with m equals 0 and to see what can happen.
Yeah.
Okay, we shall do this. We shall see what will happen in this case. But I'm afraid that in this case, everything will be so symmetric that we will lose magnetism. We shall return to one level in the theory. But we shall check this. Okay, thank you very much for this suggestion.
Can I ask you about, you mentioned the penning trap as a sort of a system you could at least visualize or apply a little bit of the calculations, right? Do you foresee any other system you could be interested in perhaps checking your results, or?
Oh, I suppose that the realistic case can be this penning trap because they exist. So,
Sure.
but we have to understand what can happen there. I suppose that this giant diamagnetism will exist, but we have to think about some suggestion what to measure with what dimensions of this trap. And this is our program for the nearest future.
Okay, and would you think that maybe a cold atom system maybe could mimic that kind of
No,
situation,
cold
or
atoms, you
not?
see, with this problem of
Let's say
charged
with
particles.
thermals,
So
for
we
instance.
need ions, not atoms, but ions. And then we have some problem because in atoms, this diamagnetism is very, very small because frequency is inversely proportional to mass. And mass of atoms is several thousand times more than mass of electron. Therefore, frequency will be small. So to see this, we need ions with zero spin in order that we could not think about spin, because otherwise spin contribution will be much higher than this. Therefore, with ion situation, we will be probably interesting, but more complicated. We have to think about this.
Sure. Thank you very much. Let's thank Professor Dodonov again. Let's finish the session.
Okay.
Just a couple of announcements. First, it's a reminder that everybody has homework today. So tomorrow morning, we have a poster session. There are 10 people answering questions about their posters. So if you could take a look at the website, see their posters, come up with some questions to ask them. You can ask them directly on the site. There is a comment box there, and you can enter your questions, and tomorrow they will be answered. And the second one is that dinner is at the same restaurant that we went for lunch. You can go directly there. I think it opens at 6:30. It closes around 9:30, 10. I'll be walking from here to there at 7 p.m. So if you want to join me, I'll be in front of the institute at 7, and then I will go there. Or you can meet me there